And if you might recall, in our last video, we talked about the full adder and how to implement the carry look ahead to improve our carry out signal to be available to our outputs to improve our circuit generation performance. Today, we're gonna talk more in we're gonna talk and we're gonna dive more into the memory side of the CPU, and that's where the file register takes over. It's the beating heart of a CPU. But first, what is even a file register? Now, imagine that we have a drawer. Let's see if we have a drawer here. We can draw something real quick. Um, this drawer, we can call it the file register. And this file register has a couple of drawers. And drawer 1, 2, 3, 4, and 5. And let's say each drawer, I don't know, they carry tools, they carry screws, and wires, for example. Now, let's say me as the technician, I want to use the tools and screws. However, I can only put one stuff at a time, so only one time to one drawer. However, I can always take multiple stuff, at least two things out. And that's exactly what a file register does. It allows us to store temporarily any value, so your processor might use it in the future. For example, let's try to make it simple instructions. So add is equal to register 0, um, st1, st2. So when the CPU execute these instructions, it is saying grab the information of drawer 1, grab the information of drawer 2, add it, and then put that information inside drawer 0. This is essentially what it's doing. So the file register is just a very fast local memory like tools on a bench, not on the warehouse, because on the warehouse will be more like your SSD, your RAM, your NVMe, because that's not inside of your CPU. It's outside of your shop. And inside your shop or your garage, you need a drawer, you need a cabinet, just like this one. And since it's inside the CPU and it's considered his short-term memory, it's very efficient and very close to where the action is. And then you might be considering, oh, so it's a file register, same as a cache. It's similar, but it's not the same. Cache is actually farther away from your file register. File register is right there in the action where everything is happening. So if we dive into our MIPS architecture, we can start talking about the concept. that surround our file register. For example, it's in the mixed architecture, is the file register is a set of register that can be read or written by supplying a register number, and each register is implemented using the flip-flops. The read ports can be implemented with a pair of multiplexers, each at Y as the number of bits. And then for if we want to write into the file register, we can implement a decoder to generate a signal. So I'm gonna present you a top view of the file register on the MIPS architecture. So this is the register file. It has two read inputs. So read register number one, read register number two. It has a write enable signal. It has two outputs. It has output number two. It has the write data that for the MIPS architecture, it's going to be a 32-bit line. It also have a register data selection. This will tell which register I want to write to. And this is our register file. Now, if we want to see internally what we have, then we can proceed and go to the next drawing. So how exactly is this implemented inside? So imagine that I have an array of registers. So register 0, register 1, register 2, and I'll generalize this. Register n minus 1. I started on 0, so if I had 32 registers, then minus 1 is 31, so that is my last register. Each one is going to have a clock and a D input signal, clock and D input signal, clock and D input signal. I'll have a decoder here. It goes from n to the 2n power. So 0, 1, 2, generalize 31. I will have the let's see, the write data, and this one will be connected to all of them at the same time. And then I have this one, register data. So if I have 31, so that's 5 bits, that's 32 bits. And then this one, it'll enable. So if I end this, and this is my write enable signal. And then this one goes here. That one goes there. And then this, I need two outputs. So in order to implement that, I'm gonna use a multiplexer. And then this is my Q. My register, my register too. So I can control this. I'll put it right here. So we can control my multiplexer. The inputs are going to be the same. Gotta be careful here. And this is going to be my output 1. And this is going to be my output 2. And this that you see here is going to be my register file. And this is what we're going to try to implement today. So how exactly are these registers implemented? So one way that we can do it is, like I told you previously, we have the use of deep flip-flops. So let's see, inside the registers, it's just a set of deep flip-flops. So remember that we have a deep flip-flop that are simply bit holders, Q. I'll make 4 bits. I don't want to make 32 flip-flops. And you know that each one has a clock. And if we want, so we have always a common clock, but then you have the gate here. You can only write to one at a time, so that's perfectly fine. I'll make another one here, another D flip-flop. The inputs can be interconnected to each other, that's fine, because the flip-flop that is going to take the input is whoever we clock. Now for the outputs, let's say we have a 2 to 1. That means it's only 1 bit. If it's 0, it controls this one. If it's 1, it controls this one. So imagine that this is a bus. So that means we have 4 sets of mux. So we have same here. So if it's 0, then you route. If it, let's see, if mux equals 0, then you route this line towards the output. And if it's 1, then you route this line. He routes the bottom one. We will have another mux here. 2, 2, 1, 0, 1. Same. This line goes to top and this line goes to the bottom. And then we have a decoder here. Same, name to 2n, 0, 1. And then you have a clock signal coming at whatever hertz you have it set. That one's going to be connected to both. So this is how the multiplexer will be internally implemented. So now that we have talked on how to implement this system, I took the liberty to go ahead and implement the circuits myself in Logisim. Here I made a very simple one to show you how actually it's working, because when we're trying to build 32 bits and 32 registers, that's a lot of bits that we have to track. However, to as a proof of concept, I'm going to show you 4 register, 4 bits. So if we go here and enable the clock, you can see that my clock is being distributed to all of the AND gates. However, they're not going through all the way to clock the registers. And if I want to select the, let's say this register that is right here, that will be my register number 1. And let's say I want to write 101, and you can see it's not clocking the register. Why is that? Well, I haven't enabled the decoder, and this is important so I can write into the file register. So if I click 1, it will load those values to my file register, register number 1. And I can turn it off, and it will hold those values even if I serialize my write data. So register number 1 has that value, that is 10. It has value number 10. As you can see, there's nothing in my outputs. Why is that? Because my read register number 1 is trying to read from my register number 0. So if I select 1, then the value that is in here will be transferred to my output. Now if I want to write into my register number 3, so I select number 3. Let's say I want to write F or 1111 for 15. Load it, disable it, and I can serialize this. It won't override my registers, and I can delete that too. And as you can see, if I want to read from register number 3 my values, I will select 3, my register 3, and you can see I have the value of my register is on the output, and the value of my first register is on my output number 1. And if I also want to read from my last register, there you go. I got 111 from my last register. I got 111. And if I want to read from my register number 0, I have a 0 because I have a 0 here. Now that I have shown you how a simple register file works, I can show you a more involved one, that is a more complex one. Here I have 1, 2, 3, 4, 5, 6, 7, 8 bits, and 1, 2, 3, 4, 5, 6, and 7 registers. And the theory is the same one. If I want to write into my first register, because this is register number 0, I will do the same concept. I will enable the clock, and you can see it's clocking. And let's say I want to write the first bit 1, 1, 1, 1, the first 4 bits, and this is actually register number 1. I try to implement this as close as the MIPS architecture, so my register number 0 is always going to be 0. So I have to select here, write into register number 1, enable it. It's going to load those values into my register number 1, disable it. And in order for me to display it on my output number 1, I have to select output register number 1. So as you can see, this I can delete it now. It won't override my register, and output number 1 selects 111100. So if I want to write to my last register, so my last register is register number 7. I want to select all of the values and enable it. My last register is going to get loaded with all the ones. Disable it. I don't need it anymore. Let's read last register. As you can see, I have register number 1 and register number 7. Register number 1 has 111100, 11100, and my last register has 111111, and I can output both of them. And this is a more medium, more proof of concept register file. And now that I have shown you, I can show you the real implementation that is 32 registers, and each one is loaded with 32 bits. One way I can show you that is that I can open this one. As you can see, I have 32 bits on each register, and each one has 32 bits. How many bytes is this? So I have 32 times 32 bits divided by 8 bits, and we're talking about 128 bytes. And it's the same concept. If I want to write data to my let's say to my second register, and that will be F. Close this, and if you can see, I have selected F here. And this is a good implementation of my file register. I do have to change the first register because register number 0, according to the MIPS architecture, should be a 0, but that's fine. It's very simple to implement. I can either remove this one from here and tie it to 0, or I can actually I might do that real quick, and then let's see. Uh, 32, and I will say that it's 0, and then feed it. So if I go here and I want to read from my bit 0, I will also always have a zero. Maybe do some cleanup here and delete this. It's fine to leave it hanging. In real life, you will not leave any output floating. You could pull it down to ground, but for the effect of logarithm, you can do this. And that is perfectly fine. And it won't affect the circuit at all. And like you can see, there's no way for me to write into register number one because I want that register to always be zero. So if I put 00 and I try to clock it, you can see my output never changes because it's always zero. It's important to remember that my flip-flops they are positive, so it will only happen on the rising edge of the clock and only if register write is on. And if you go here, my register write is 1. The file register, um, even though it looks convoluted, it's very fast. It's small, but it's also faster than RAM because it's like right there in the action. It doesn't have to deal with addressing delay or cache hierarchy. It's right next to the LAU. It's always ready at all times. All of this is combinational logic. And if we didn't implement this, the CPU will be very slow. It will waste a lot of cycles just looking for data that is available right next to it. With this, everything stays efficient, it stays streamlined, and it's like going back to our initial analogy. It's like when the technician needs a tool, it just go inside the drawer and grab it instead of going to the warehouse. If you learned something new today, just go ahead, subscribe, hit the like button, subscribe to Black Body Engineering, and dude, let's share this with more people. My goal is to create a series that will help me understand this concept better because this is something I love. Um, I'll want this to be shared and understood by many more people because I love it.